Are these the details I gave you? Is this right? Does that look like it's the question? Yeah? Okay, good. Focus, directrix, eccentricity, okay? Just in case maybe you were catching up, let's just do this from scratch. Okay, we can work this out. This is defined by this equation. Okay? Because that's what the eccentricity is. It's that ratio. Okay? So to make things a little easier for us to work out, I'll just chuck that over the other side so I don't have to deal with fractions. So I have a distance formula on this side and I have a perpendicular distance formula on this side. Let's quickly compute it. Okay? What do I get on the left-hand side? X minus 4 squared plus y squared. Okay, good, that's fine. 2 times what? Absolute value of x minus 1. Where did that come from? That came from this in general form, right? It's pretty easy, so that's why I don't need to rewrite it. All divided by... Well, when you do the square root of a squared plus b squared here, your a and b are going to be 0 and 1. So you actually just get 1 there, don't you? So I should actually write it though, just because that's the full formula, okay? Good, now what? Square the lot, okay? I might as well expand this while I'm at it. That's going to be 8x, 16, 1 squared. What do I get here? 2 becomes a 4, and then this is going to become x squared minus 2x plus 1. That's a terrible 2. Okay. Happy so far? Okay, let's expand this out. X squared squared, or x squared. So far, so good? Okay, any suggestions? I can simplify this in a number of ways. What ought I to be working toward? What kind of last line do I want? What do you think I should have on the right-hand side? We want the constants on the right-hand side, yeah? That's what we've been working at so far. So, run out of space here. The constants here, I've got a 16 and a 4. So I'm getting minus 12 on that side. Does that look right? Yeah. Okay, now what? Gather everything else on the left. So let's see. I've got 4x squared here and one of them there. So I have minus 3x squared. I've got 8x and I have 8x again. Negative 8x on both sides. Okay. So they both cancel. That's nice. You'd almost think that the numbers were picked deliberately to do that. Then I have a y squared. That's it, isn't it? Okay, now you told me just now you wanted a 1 on this side, right? So if I divide through by minus 12, I'm going to get x squared on 4 minus y squared on 12. Does that check out? Are you happy? Okay, now, what is this thing? It is very close to an ellipse, isn't it? Which I suppose we ought to expect because we started at a form that's close to an ellipse. But it ain't an ellipse, how can you tell? Because of the negative, okay? So something else is going on, right? Now, immediately you can tell it's not an ellipse, but there's a domain restriction going on because there's an even power of y. Okay? So let's go ahead and work out what the domain restriction will be, and then that'll give us some clues. Okay? I want this guy to be the subject. Once I know he's the subject, everything else has to be positive. Okay? Watch. Minus y squared on 12, kick this guy over to the other side. Yeah? I probably want this to be positive, like so. So this turns around. Okay, great. Now, forget about the 12 for a second, because really, can you see that 12 doesn't make a difference to whether it's positive or negative? It just makes it a bigger positive or a bigger negative. More negative. Okay? So therefore, this thing here has to be greater than or equal to 0. Otherwise, this doesn't exist, full stop, for real values anyway. Okay? So I can say the domain will be defined by this guy being greater than or equal to 0. You happy with that? Otherwise, it doesn't exist. So multiply through by some nicer numbers, like so. What's this look like? There you go. It's down minus 4. which means the roots are minus 2 and 2. Okay? So therefore, the actual domain is where that thing is positive or equal to 0, right? Namely this part and this part. Okay? So now we know the domain is, how would you write it? X is less than or equal to minus 2. Or the other side. Okay. There's the domain. Now, by the way, one of the reasons why I started with this is kind of an unusual place to start, but it immediately tells you you can't exist in here, right? So there's not much point looking for a y-intercept, because there isn't one. It can't exist at x equals 0, right? That's outside the domain. So I can't find a y-intercept. What can I find that will help me work out the shape of this thing? I can work out an x-intercept, can't I? How do I do that? You go y equals 0. Where shall I put it? I can fit it in here. Y equals 0. That tells you x squared on 4 is equal to 1. X squared is equal to 4. So that already tells you minus 2 and 2, which are the very edges of our domain. Those are your intercepts. Okay. How else can we work out what this thing looks like? Who plugged in values? Who just plugged in values? Did anyone do that? I'm interested because those of you who plugged in values probably have the most accurate shape. I'll talk about why that is in a second. Okay. I think I heard someone say limits. Did I hear someone say limits? Yeah. Okay. Good. I think limits is a good idea. But how do we do them? What kinds of limits would we form? Limit of what? As x approaches infinity. Okay. Of what? What am I going to put in there? Now, it'll probably help you if you take probably this line here. Okay. Now, don't forget, you're going to get a lot of symmetry happening. Every time you square something, you're going to get symmetry. And I've got two things squared, right? So you're going to expect heaps of symmetry, right? But having the squares in there makes it hard to work with the limit. Because what do you put in? I've got 2 things, or 4 things, right? So what am I going to use? I'm going to rewrite this in a way which will make it a little easier to see. So, if I make y the subject, okay? If I make y the subject, first I suppose I should multiply 3 by 12, which will give me that. You happy with that? And then I'll take the square root. There's what I'm working with, okay? So I'll take the limit of that. 3x squared plus minus 12, okay? I don't need to do both, because once I've got one, I'll have the other one, I just have to slap a minus sign on it, okay? What's going to happen to this thing? What can you tell me as x approaches infinity? Because this isn't the kind of limit we're used to dealing with, really. Let me pose this question. What will happen to this minus 12 as x approaches infinity? What happens to it? It becomes trivial, doesn't it? Because this guy is becoming millions and billions and trillions, and this guy's still minus 12. So he becomes insignificant. So in some senses, I can say this. Aren't I? They're going to have the same limit in the long run, which is what I'm interested in. Now that thing's actually very easy to work with, right? It's a product underneath the square root, so I can break that apart. Square root of 3, square root of x squared, yeah? That root 3 is just a constant, so I'll just chuck it out over here. Square root of x squared is, oh, so close. The absolute value of x, isn't it? Because it could never be negative. Whatever you throw in there, it will still be positive. Okay? Should catch that. That's one of the definitions of absolute value. Anyway. All right, so therefore, what's this thing going to look like? Once you evaluate this, that's just a straight line. What's root 3? It's like 1.7-ish. So it's a steep thing. So it's going to look something like this. notice I'm only interested in this side because that's the side that I'm comparing. Okay. Now you can go ahead and you can do the rest of the limits. Okay. You can consider what happens to negative infinity. You can consider what happens when this has a minus sign on the front. After you go through all of that legwork, you will end up getting these two. Okay. So I have these two asymptotes that are going to shape my relation. Okay. Now what? It looks pretty bare, but believe it or not, I have all the information I need. Okay. In fact, all I really need to do is draw one part, namely this part. Okay. Now you can plug in some values to see that it's going to happen. Right. There are no stationary points. You can differentiate and see what happens. But remember how I said you've got a y squared and an x squared. So you're going to have symmetry across the x-axis. Sorry, that's the y-axis. But you're also going to have symmetry across the x-axis. So you take this shape and you reflect it down. And then you take that shape and you reflect it across. Like so. There's the shape I've got. And this is what we call a hyperbola. This is the last conic section. Okay? Now, some of you are ahead. All of the stuff I just did on the board, you're already done. The question, do you remember what question I posed to you after you got a drawing? What was the question?
Lines reversing.
Yes, okay, alright. So, what's the time? What time does lunch end?
7.
10 minutes?
I don't
10 minutes? 10 past? Alright, we don't have time. Okay, now, in case you weren't following, we're trying to think about this progression. This is what we're thinking about, okay? Now, by the way, just as a side note, if some of you are looking at the textbook, you might be like, whoa, we're at the hyperbola already. There's still stuff about ellipses to talk about, namely the polar definition, and parametrics and all that kind of thing. We will get back to that. But because we're sort of making this progress, I wanted you to see this shape, so you sort of aren't waiting until the very end of the topic before you see what this section is. Okay. Now, what are these shapes? They have names. When x-interest is 0, we have the special case of circle. Okay, so it's going to look something like that guy. Okay. When x-interest is between 0 and 1, you get the ellipse. So what happened was, if we had vertical directrices, it starts to stretch out like so. Okay. What about this shape? Parabola. So you're getting this. Now you'll notice I've drawn it sideways rather than upright. Why? Because where I was coming from was having these vertical directrices, right? And I have one on the other side. Well, if your directrix, parabolas only have one. If your directrix is vertical here, then your parabola will be sideways, okay, from what we're used to. Now what have we got? The very last one, we've given a name, we call it the hyperbola. So it looks something like this. Okay, now, my question was, why does it do this? Why is it in this order? What's going on? You can almost see what's happening, can't you?